So today's lesson, today's Wednesday, March 25th. It's separation of mixtures. So we're continuing on the right-hand side of our matter chart from the last meeting. So we're talking about the different types of mixtures. Again, mixtures are not pure substances. Depending upon who makes them, they could be made differently. There's different concentrations, which we'll get to next week, of mixtures or specifically solutions. So again, a mixture are two or more substances that are physically combined. They're not in definite proportions. And the two major types of mixtures are homogeneous and heterogeneous. So there's basic properties of both of those. So let's start with heterogeneous mixtures. Those are ones where you can see the different particles. Like one of the examples from the assignment that was given on Monday was a smoothie, where you can see the different pieces of the strawberry inside of the smoothie, and you can filter out the chunks of the banana and the strawberry in the smoothie. If you have cereal and milk, you can filter it. You can see the different particles. You can point to it and say, there's the cereal, there's the milk. For sand and water, you can see the sand. So the basic concept of a heterogeneous mixture is the substances do not dissolve, and you can separate by filtering. Okay, and for a homogeneous mixture, we mentioned different types of homogeneous mixtures, like salt dissolved in water is a very common one. Anytime you see that something is aqueous, aqueous means dissolved in water. So whenever you're given a problem where it says aqueous, that means dissolved in water, and anything dissolved is a homogeneous mixture, and you can separate by distillation. Another separation technique that you saw on the handout for today, if you opened it, was chromatography. And I don't have paper chromatography. Let me just admit these two people in the waiting room. Okay, so I don't have chromatography paper at home, and I tried to do it. It didn't work out very well. But typically, if you have chromatography paper, this green marker, you can't really see it too much. I do see it separating out into a little bit of yellow. But typically, if you do it in school with the chromatography paper, you'll see it separate into its components of yellow and blue. Similarly, I tried it with a purple marker, and the components of purple, are red and blue. I can see a little bit of blue in here, but it's hard to see on my poor camera system that I have set up here. So there was a question about chromatography. So if you had trouble answering that chromatography question, again, this is chromatography. It's very similar to something you learned in biology with the DNA separation. It's separated by different attraction to the paper. So different colors will have different attractions to that paper and will run up higher or lower. And with DNA separation, you might have learned about gel electrophoresis when you were in a living environment. It has a similar concept where you're separating out the different components of a mixture. So all of those that's another example of homogeneous mixture. You can't see the blue or the yellow until you do that chromatography technique. Distillation is by different boiling points. If you don't have different boiling points, you're not going to be able to separate it. But the major concept with the homogeneous mixture is that it's dissolved, and there are different concentrations that exist. So if, for example, okay, right now I have, this is cold tea, and then I have a room temperature tea, and then I have, oh, this glass is kind of hot. So this is a hot tea. So what I'm going to show you here is that based on the temperature affects the solubility and the concentration that you can make your different solutions. So if I take a packet of sugar and I go to dissolve it in this cold tea here, I'm hoping you can see it. It's kind of difficult to see. Oh, you know what? If I put it closer to a different color, you might be able to see it more. So the sugar settles down to the bottom here or precipitates. So some of it will dissolve, but not much of it. Not much of it is dissolving. Even if I were to stir it, it's really not going to dissolve so much because it's cold. So when you have a cold temperature substance, it's very difficult to get it to dissolve and have a high concentration. So if you want really, really sweet tea, you might need to heat it up first and then take a sip of it. So let's take the room temperature one. Okay, so the room temperature one, a little bit more of it is dissolving, but you still see that you have a precipitate settling to the bottom, but less of it is precipitating than that was in the cold tea. Then if we take our hot tea, take the tea bag out of it. So if you see there's no precipitate at the bottom of this one, all of it did dissolve. I can actually add a second packet of sugar. There's a second packet of sugar, and it is still dissolving in there. I still don't have a precipitate. So this is getting really highly concentrated here because the temperature is higher. So the concept is that as the temperature increases, the concentration of the solute or the sugar that's dissolved in this solution will increase. I can probably add a third. Let's see what happens if I add a third. So I dissolved a third packet, and most of it is dissolving. I'm starting to see a little bit settling to the bottom there, which means that this solution is probably getting saturated or full of solute to the most that it could possibly hold at this particular temperature. If I heat this solution a little bit more, I might be able to dissolve a fourth, a fifth, and a possibly sixth packet of sugar. So again, as you increase the temperature, the solubility of that sugar is going to increase as well. So if you use table G on your reference tables, you don't have one there, that's okay. I don't even know if you can see this on there. That's hard to see. Let me see if I can draw one that's similar. I should have tested that out first, huh? So if you look at table G on your reference tables later in the day, you will see that the y-axis is called solubility, or the amount of solute in grams that will dissolve in, and it says 100 grams of H2O. So this table G, is based on if you have 100 grams of water. So if I have 100 grams of water, this is going to tell me how many grams of that solute I can dissolve. So let's look, for example, at, KNO3. So KNO3 kind of looks like this on your reference tables, where at this point here, it's telling me I can dissolve about 15 grams of KNO3. This is KNO3. In 100 grams of water at 0 degrees Celsius. This is the temperature in Celsius. Now, if I increase that temperature, let's say to 10 degrees. If I increase it to 10 degrees Celsius, now what this curve is telling me, if I read it and I go all the way to the left, tells me I can now dissolve about 25. That's 25 grams on your reference tables. I know it's kind of hard to see here. So as I increase and I make the temperature higher, more and more and more will dissolve. Any single place on this curve is the most you can dissolve at this given temperature, or where it is saturated. So if, for example, at 10 degrees Celsius, if I only put 15 grams of KNO3 in there, it will not be saturated because it can hold a total of 25 grams. So I can add an additional 10 grams of KNO3 until I get to that 25-gram point. Once I add more than 25 grams, you're going to start to see that it's going to precipitate to the bottom. So once you go past that maximum amount or that saturation point, you're going to see precipitation happen because you cannot dissolve any more at that temperature. The only way that you can get more to dissolve is to increase that temperature, and then more and more and more can dissolve. Okay? So if you look at table G, again, this is so hard to see on there, you will see that different substances have varied solubilities. Most of them increase with temperature. That's if you're dissolving a solid like KNO3 or salt or sugar. As you increase the temperature, solubility will increase. If you look at table G, you'll have a few exceptions, like for example, ammonia or sulfur dioxide. Here's what sulfur dioxide kind of looks like, where it decreases. That's for a gas. So when you look at that, or if you look at ammonia, they have the opposite effect. So gases decrease in solubility as the temperature increases, and solids will dissolve better in hot liquids. Okay? So overall, that's what we're talking about today. We're going to continue with our discussion on using Table G in problem solving on Monday. But today's lesson is mostly focused on different types of mixtures, what makes a mixture. You have the heterogeneous one that you can separate by filtering. You have the homogeneous one that you can separate by distillation. And for homogeneous mixtures, they have different solubilities or different amount that can dissolve based upon the temperature of your solution. Okay, so on Monday there will be questions about solubility on the Google form. Today's is mostly about separation of mixtures. If you do have questions about that form, I'm going to go onto our chat area right now and log off of the Zoom. Again, I will be posting this Zoom on my YouTube channel. It's not a very fancy YouTube channel, but it works. And you can rewatch the videos, take notes on the videos, watch the videos while you are doing the Google form handout. But make sure you like and subscribe so it's easier to find. Okay, I'll talk to you all on the chat soon.